Hey guys, Mr. B here, and in this video we're going to be going through chapter 14.1 on work and power. So let's get into it. Now, these two words, work and power, are two words that you probably have used all the time in your everyday language. I know the word work is used all the time, but in physics and in science, these two words don't quite mean the same thing that you think they mean. So work, of course, when you think of the word work, you might think of going to a job to get paid. You might think of doing homework at home. You might think of work as just basically doing something that requires some amount of effort that usually is tiresome or people don't want to do, right? However, in physics and in science, work is very specific, okay? So, recall that in the previous chapter, we learned about forces and that objects will move when unbalanced forces act on them, or their motion will change when unbalanced forces act on them. In science, the word work is the product of force and distance. So basically, in science and physics, the word work is something that is done when a force acts on an object in the direction that the object moves. So basically, work is something that is only done when an object is pushed or pulled and it moves in the direction that the force is pushing or pulling on that object. So when you go to work, for example, like a job, you may or may not be doing work at your job. Are you applying a force to an object? Is that object moving in the direction that you're applying a force? If not, you're not doing any work. When you're sitting at your desk and you're doing homework and writing on a piece of paper, you're doing work on the pencil because you're applying a force to the pencil and it's moving. However, the act of actually writing something isn't actually work in the physics sense of the word. So here's another example. So here we have a weightlifter who has a barbell over his head, right? He's holding it up over his head. I'm sure it's very heavy. And he is standing in place as he holds this barbell over his head, okay? Now, this might be a lot of effort. You know, his muscles might be straining. He might be like, as he's trying to hold it up over his head. However, the barbell is not moving. Okay, it's motionless. He's holding it above his head, not moving. Therefore, he is not doing any work on the barbell. Now, initially, when he picked it up off the floor and he lifted it up over his head, he was doing work. He was applying a force in the upward direction and the barbell was moving upwards. But once he gets up to the top and he holds it up here and it's no longer moving upwards, he's not doing work anymore. Now, he's still applying a force up, okay? He has to. If he doesn't apply a force up, it's going to fall on his head, right? Because gravity's pulling it down. So he does have to keep pushing it up, but if it's not moving up, he's not doing work anymore. Even though it might be very strenuous on his muscles, he's not doing work in the sense of this definition, okay? So for a force to do work on an object, some of the force must act in the same direction as the object moves. If there's no movement, no work is being done. All right, so work depends on direction. The amount of work done on an object, if any, will depend on the direction of the force and the direction of the movement. Any part of a force that does not act in the direction of motion does no work on an object. Okay, so another example. Let's say that you are carrying groceries into your house, right? So you've got a bag of groceries and you're walking in your house like this. Are you doing any work on the groceries? So I'm going to stand up here and I'm going to back up a little bit. So let's say that we're carrying our groceries, right? We're carrying them like this and we're walking like this, right? Are we doing any work on the grocery bag? You might think, well, yeah, of course, because they're heavy and I got to carry them inside. But think about it, right? I'm holding the groceries like this. Am I moving them upwards or downwards? No, they're staying in place. If I'm walking, right, if I'm walking like this, my body's moving that way. But the groceries are not going up or down. They're going sideways, but I'm not pushing them sideways. So when you hold a bag of groceries, you have to pull upwards or push upwards. Because if you don't push upwards, they're going to fall to the floor, right? Because gravity causes them to fall. So you have to apply a force upwards to keep them from falling to the floor. However, if you're walking, they are moving sideways. Yet you are applying a force upwards so that they don't fall. And the direction that they're moving and the direction of the force you're applying are not in the same direction. Therefore, you're not doing any work on the grocery bag. As much as you might think you are because they might be heavy, you're not. The force that you're applying is not in the same direction that the grocery bag is moving. Okay? So, again, it's a different way of thinking about work, or at least it's different from the common use of the word that we are used to seeing, but it's not that hard to get the hang of once you understand it. So in the previous example, the weightlifter, as we mentioned before, although the weightlifter had to do some work to get that barbell up over his head, he's not doing work while he's holding it over his head, right? But he did do work as he lifted it. So to calculate the amount of work that something is doing or someone is doing, we have a very simple equation. Okay, work is equal to force times distance. Now work is going to be measured in the units of joules, and this is going to be brought up here in a second. So work is measured in the unit of joules. Force is measured in the unit of newtons. Let me shift this over here. And distance is typically measured in the unit of meters. Okay, so this is our equation for work. The joule is usually abbreviated with a capital J. It is the SI unit of work. It's also the SI unit of energy. The unit that you're probably more familiar with is the calorie. And when I say calories, I don't mean like nutritional calories, you know, like your food has calories. I mean thermal calories or heat calories, which may also not be a unit you're super familiar with. But regardless, okay, the unit of work is known as the joule. So when we talk about doing work on something, we will measure it in joules. Now again, using the work formula, it's pretty simple. If we want to know how much work something does, we need to take the force applied to that object multiplied by how far it moves. If we multiply those two things together, we will get some amount of work done, and it will be measured in the unit of joules. Okay, pretty straightforward. Okay, we're obviously skipping past practice problems here because those are at the end of this in the quizzes, so let's keep on going. So next thing and the last thing we have to talk about here is power. Again, another word you're familiar with that maybe you're not entirely sure what this word means, or at least maybe you think you know what it means. So of course, in our everyday language, we talk about power. Power can mean a lot of things. It could mean you're strong, right? You're powerful. Oh, you got big muscles. Power could mean that you have influence over something or other people, right? Like, for example, you know, the government has power, or police officers have power over us because they can make the laws, etc. However, and again, physics and science, the word power is something very specific, and it has to do with work. So power is the rate of doing work. So power has nothing to do with how strong you are or how how much influence you have. Power is about how fast you can do work. So basically, imagine that we have a scenario, okay? And again, I'm going to do a little bit of acting here. So imagine we have a scenario where we have two people, and they're both lifting a heavy object. Okay, so let's say this is our heavy object. And so the first guy's like, all right, ready? I'm going to lift this, and you see how long it takes me. Ready, say, and go. And it takes him like 20 seconds to lift this object. And the other guy's like, oh, yeah, nice job, man. Good work. Oh, man, whew. Great work. Okay, my turn. He's like, all right, are you timing? Ready? And he lifts it in like 2 seconds. Which one of the two is more powerful? Well, according to our definition of work, it is whichever one does it faster. So both people do the same amount of work because they're both lifting the same object, the same distance. So they both have to apply the same amount of force, same distance, same amount of work. However, the guy who does it faster generates more power because power is defined as the rate at which you do work. So the faster you do work, the more power you have, okay? So it has nothing to do with, again, strength or anything along those lines. It's all about speed. How fast can you do it? Now to calculate power, because of course it is a rate, basically to find the amount of power generated, we will take our work done divided by the amount of time it takes to do it. Okay, now power is going to be measured in the units of watts. Work, as we already mentioned earlier, is measured in the units of joules. And time is typically going to be measured in the units of seconds. Okay, so watts is our unit of power, which I'm sure you're all familiar with that unit because light bulbs, of course, are measured in watts, or like appliances and ovens and microwaves will give you how much watts they use or wattage. So that one is at least a unit that you are familiar with. Okay, So again, it's shown here. The SI unit of power is the watt, abbreviated with a capital W. Okay, so if you see that, that's what that means. It basically is equal to 1 joule per second. So like a 40-watt light bulb basically requires 40 joules each second that it is lit. All right. The last little bit here is just talking about another unit of power, which is the horsepower. So some of you may be familiar with horsepower. Of course, motors and engines and things like in cars and boats have engines that are measured in horsepower. Back in the day, the horsepower was actually like how much power one horse could generate. Nowadays, it's obviously not quite that anymore. But regardless, a horsepower is just a much larger unit. So 1 horsepower is about 746 watts. So we oftentimes will measure engines and things like that in horsepower, primarily because they generate so much power that if we measured them in watts, the number of watts is very large. So the horsepower is just kind of like a more condensed unit because it's a bigger unit, right? It's kind of like saying my engine is, 746,000 watts. That's how much power it generates versus like 1,000 horsepower, okay? Anyway, all right. So that is it for this section of notes. Hopefully you have a good understanding here of what work and power means. We'll be doing some things in class, of course, to practice this, so maybe that will help you more. But either way, if you have any questions, as always, feel free to email me or reach out and make sure you get those questions answered. All right, guys, thanks for watching. That's the end for this one. See you in the next one. Bye.